Dear viewers, today we will learn the time required to achieve the desired drying in wet solids. To learn how to calculate the time required, we must know the rate of drying equation first. What is the rate of drying equation? Here it is. The rate of drying R is equal to minus SA divided by dx, multiplied by dx by d theta. Let us get the terms involved known. R, naturally the rate of drying. S is the mass of the dry solid. A is the surface area of the wet solids exposed for drying in contact with any drying gas, for example dry air. Dx is the moisture removed, x1 minus x2, where x1 is the initial moisture content and x2 is the final moisture content. So it is x1 minus x2, that is the moisture removed, and d theta is the time span elapsed in removing that moisture, means time required to achieve x1 minus x2, that is time required to remove that much moisture. So R is equal to minus S divided by A dx by d theta. Negative sign indicates that the moisture is getting lost, that's why the rate is decreasing. That's the only indication the minus sign indicate. Now if we rearrange the equation, it would be d theta is equal to minus S divided by A into dx by R. This R comes to this side and the d theta goes to that side, and we put an integral. We put an integral sign there to integrate the whole equation. So this is integral d theta, which is equal to minus S by A integral x1 to x2, where x1 is the initial moisture content and x2 is the final moisture content, and dx by R. R is the rate of drying. Simplifying this equation, we get theta is equal to S divided by A integral x2 to x1 dx upon R. Now the minus sign has disappeared because we have changed the limit. We have interchanged the limit. By integral methods, the lower limit should be at the bottom and the upper limit should be at the top. So x1 is greater than x2 because x1 is initial moisture content, and after removing the moisture we get the lesser amount of moisture content, that is x2. So x2 is the lower limit and x1 is the upper limit. While interchanging them, we will be changing the sign. So this minus sign disappeared and the limits were interchanged. The final equation we got is theta is equal to S divided by A integral x2 to x1 dx upon R. Now there are three cases over which we can calculate the theta. Theta is the time required for drying. It depends on the drying application we receive. Three cases of drying applications are there, or in simple manner, three cases of drying are there. The first case, what is that? If you look at the rate of drying versus moisture content, that is, this is the drying curve. If you look at this drying curve, x1 is the initial moisture content and x2 is the final moisture content. Means the problem is we have to remove the moisture from x1 to x2, that is, this much moisture we have to remove. Now we are able to see this removal of moisture is along the constant rate drying part of the drying curve. It means that the rate of drying is constant because it is falling on the constant rate drying period. That's why if RC is there for this much duty of drying, duty means the purpose of drying from x1 to x2. So for this much duty, if the rate of drying is RC and which is constant, if we put this RC in place of this R, we will get this equation. This R will be taken out of the integral sign because it is constant. RC is constant. So we have taken it out of the integral sign and we put it like this: S divided by ARC into x1 minus x2, where x1 is the initial moisture content and x2 is the final moisture content. So if we are asked to remove the moisture within the constant rate period of the drying operation, we have to apply this formula to calculate the time required for drying. S divided by ARC into x1 minus x2. x1 minus x2. Initial minus final. This is the case 1. Now case 2. What is that? The case 2 is that the initial moisture content is x1 and the final moisture content is x2. So we have to dry the solid between these two. Means we have received such a wet solid whose moisture is already been removed till this point, beyond the critical point. Constant rate period has already been elapsed. We have received a wet solid in such a way that it contains a moisture equal to x1. And from x1 to x2 we have to achieve. We are able to see that this difference or this moisture removal falls in the falling rate period or falling rate region of the drying curve. It means that we have to use this R, which is the drying rate for falling rate period. Therefore, we got this equation. If we refer this R in place of this R in this formula. But there is a relation between this R and RC. That relation is R upon RC is equal to X minus X star upon XC minus X star. We know X is what? Any moisture content. Any moisture content. And X star is equilibrium moisture content. XC is critical moisture content and X star is the equilibrium moisture content. How R upon RC this ratio is related to this? It's just a game of trigonometry. See, what is this ratio? R upon RC is R upon RC. Right? This R upon RC. What is this R? This R is equal to this height. Right? And if we consider this as a right angled triangle, if we consider this as a right angled triangle with 90-degree angle here, and if this would be theta, here theta is not time, here theta is a trigonometric angle of this triangle. So if we apply a formula of tan theta, what is that? It's sin theta upon cos theta. Sin theta upon cos theta. Ultimately it would become this side upon this side, right? This side upon this side. This side is what? R. And this side is what? X minus X star. Right? R X minus x star. Similarly, with this triangle, with same theta, we would get this RC upon XC minus X star. This RC upon XC minus X star. My point is that if you want to replace R upon RC by this term on the right hand side, we just refer two triangles, the first triangle and the second triangle, and you apply tan formula. After applying tan formula, you just try to put the results in this ratio. You will definitely get this ratio. It is beyond the scope of my video now, because it will consume a lot of time and you are quite wise to solve this. Okay, good. So ultimately, what I get, this R, what is that R? This R is nothing but this R. So this R to be placed in place of this R. So this R would be equal to RC into this ratio. RC into this ratio. So ultimately, I am putting now this R in this formula. So if I put in this formula and solve, I will get this equation. Again, this is beyond the scope of my video. You are quite wise, you can do it, because this is simple mathematics. I am not here to teach you numerator, denominator, multiplication, division, plus and minus, nothing. I am here to teach you the concept. Okay, so R upon RC, ultimately R gives RC into this much, and if you put this value of R into this and solve, we will get this value. So this is the time required to calculate the drawing in falling rate period region. This was constant rate period region, the drying time for that, and this was the falling rate period and the time required for drying in that region. Now there is one more condition, one more case, and what is that? It's the combination of both constant rate period and the falling rate period. See, the material, the wet material contains moisture equal to x1 and we have to dry it to x2, right? So from x1 to x2 we got both the regions, the constant rate period and the falling rate period, right? So simply it is the combination of these two cases. It means that the time required to achieve this much moisture removal or this much drying will be the combination of these two equations. That's why this is QC. Here it is represented by theta only. Here it is represented by theta only. We can represent them as theta C and theta F. So ultimately, if we combine these two, we will get the final equation to calculate the time required for this much drying for this third case. So you just add these two and you will get the resulting equation, which would be the equation to determine the time required to achieve desired drying. Got it?